So in today's video, we're going to be looking at something called the Gram-Schmidt process. What this does is it takes some random basis for a subspace of Rn. So it could be all of Rn or it could be just a subspace of Rn. And we have this random basis for it. What we would like is to have an orthonormal basis for this subspace. Okay, so at the moment, like, it's not even orthogonal, so if you dot product any of these basis vectors together, you're not going to get 0, most likely. So it's not orthogonal, and it's definitely not orthonormal because it's not orthogonal, and the vectors don't have magnitude of 1. So what we would like is to take this basis for the subspace of Rn and turn it into an orthogonal basis, and then turn it into an orthonormal basis. Question is, how do we do that? Well, we can go through this process, and once you get the hang of it, this process is very, very repetitive. You just have to know what the formulas are. I'm going to do this for a two-dimensional subspace of, in this case, R3. They've got an example in the textbook that I think is example 2 in this chapter that goes through a three-dimensional subspace of R4. Okay, I mean, you could have a two-dimensional subspace, a one-dimensional subspace. I mean, a one-dimensional subspace, of course, it's going to be orthogonal anyway. But you can do a two-dimensional subspace, a three-dimensional subspace, whatever it might be. But if you want the three-dimensional version of this, go and look at example 2 under this chapter. But I'm going to just do the two-dimensional example here so you can get a feel for it, and then we can expand and generalize. So let's say that you have some subspace. You've got a subspace, we'll call it W, and it's spanned by these two vectors. So I'm going to have 3, 1, 0 and 8, 6, 5. Okay, those two vectors are going to form the basis of W. So these are the basis vectors for W. So they span and they're linearly independent. Okay, now we know that W is a subspace of R3. Okay, I should actually put it's contained in R3. Okay, it's not going to span all of R3 because we've only got two vectors here. In order to get all of R3, you'd have to have 3 linearly independent vectors. So we know it's a subspace. What we would like is to find an orthogonal basis for W. So I would like two vectors that still span W, but such that they are orthogonal. Okay. The way that you always start out with this is to label your vectors. Okay, so I'm going to label them x1 and x2. So this vector is going to be x1, this vector is going to be x2. Always leave x1 as it is, and you're going to base everything off of x1. Okay, so x1 is always going to stay exactly as it is. Then you're going to adjust all other vectors, all other basis vectors, to be orthogonal to that one vector. So you always start out, in this case, I'm going to say we want to find W, which is the span of, we'll call them V1 and V2, where V1 and V2 are orthogonal. So I'm going to find this orthogonal basis. Now we know that if V1 and V2 are orthogonal, we already know that they're linearly independent. We did that before. So I know that I'm going to have two linearly independent vectors that span the space. Therefore, they're going to form a basis and they're going to be orthogonal. So we're going to get an orthogonal basis. Whenever you start out, always V1 is always going to be x1. Okay, you always leave the first vector alone. The question is, what is V2? Well, I need V2 to be orthogonal to V1, okay? How do we do that? Well, x2 at the moment, I've drawn this picture on the first page of my notes. So if you want to go ahead and look at that picture on the first page of my 6.4 notes, it makes it way easier if you can actually see it in front of you. It is kind of a difficult thing to draw. So you'll see here, okay, the purple part, okay, is all vectors spanned by x1 and x2. So I can write x1 and x2, take any linear combination of them, and I will get a vector that lands in that purple space. Okay, it's a plane spanned by x1 and x2. So that is W. W is the purple part. Now, you'll see that x1, it has no z component, okay, because x1, which is v1, is just 310. So it's only in that xy plane. So v1 is going to equal x1, which lands in that xy plane. Now the question is, at the moment, x2 is not orthogonal to x1. Okay, so we need to do something to x2 in order to get a vector that is orthogonal to that v1, that x1. Okay, so what I'm going to do is I'm going to project x2 onto that line that is spanned by x1 or v1. Okay, so I'm going to find the projection of x2 onto the space, in this case it's a line, spanned by v1. Okay, so I'm going to project it down, and that projection is going to be called P. So I'm going to say P is the projection of x2 onto, we'll call it W1, okay, where W1 is the space spanned by P1. Oh, spanned by V1, sorry. Okay, so W1 is the space that is spanned by V1. In this case, if you're spanning, the space spanned by one vector is just a line, okay? So P is the projection of x2 onto that line. It's the closest point to x2 that lands on that line. Now, if you look at the way that we add and subtract vectors, okay? If I take x2, okay, and I subtract P, okay? So I've got x2, okay, I've drawn in a line, an arrow there, just so you can kind of see how it goes up. So x2 goes up. P, because I'm subtracting P, if I do x2 minus P, okay, P is going to bring it back. So it's going to hit where V2 is, okay? It's going to hit, in this case, it's actually that Z axis, okay? It's going to bring it back, okay? And that is orthogonal to that space spanned by V1. So if you look at where V1 is, this isn't always the case, but it is in this case because we've got no Z component. But if I look at where V1 is, and the space spanned by V1 is that whole line, so you can even bring it back if you want. I've then projected x2 onto that line to the point P, okay? So I've got the vector x2 and I've now got this projection vector P. If I then do x2 minus P, I'm going to call that V2. And you'll see from this picture that V2 is orthogonal to V1. Okay? So, because of that, okay, you can go ahead and say, okay, well, V2 is orthogonal to V1, and V2 and V1 still span that whole space. Okay, I can get any vector I want by taking a linear combination of V1 and V2. So they span the space, they're linearly independent, and they're orthogonal to one another. So I can say that W is equal to the span of V1, V2, because they are orthogonal vectors, they're linearly independent, and they span that space W. Okay, it's easier to see when you look at that picture. Okay. Now the question is, how do I find V2? Well, V2 we said was x2 minus this projection, where P is the projection vector of projecting x2 onto that space spanned by V1. Now, if you remember when we did that before in 6.3 with orthogonal projections, that's just x2 minus, now, the projection of x2 onto V1, okay, onto the space spanned by V1, would be x2 dot V1 over V1 dot V1 times V1, okay? So to find V2, you need to know what V1 is first. This is very much an iterative process, okay? You have to find, if you have more vectors here, let's say you had a three-dimensional subspace, you'd have to find V1 first, which is always x1. Then you find V2, which depends on x2 and V1. Then you'd have to find V3, which would depend on x3, V1 and V2. Okay, so you always have to find the V's in order because they always depend on the last one, because you have to make sure that the next vector you find is dependent and is orthogonal to the other two, okay, or the other however many there are, okay? So you always go in order. If you were to expand this, let's say, I'll let you guys go ahead and do this. If you were to actually find this, it comes out to -1, 3, and 5. So -1, 3, 5, and our original vector 3, 1, 0, that is the orthogonal basis for W. Okay. Now, if you had the three-dimensional space, okay, let's say you had a three-dimensional subspace of R4, R5, whatever it may be, you would have to keep going. So you would say, okay, in that case, V1 is still X1. Then V2 is X2 minus, I'll call it P1. That's the projection of X2 onto this space that is spanned by X1 or V1. Okay. Then if we kept going, V3, okay, you can't, it's very difficult to draw this. They have got a drawing of this on that example too in the textbook. It's just very difficult to draw once you get past 2 dimensions, but they've given you a rough idea of it for the 3-dimensional case. So X3 minus P2. Now this time, P2 is the projection of X3 onto this space W2. Now W2 is the space spanned by both V1 and V2. Right, if we think about this, okay, we found V1. We already know what V1 is. V2 must then be orthogonal to V1 by construction. Okay, you have to make sure that they're orthogonal. Okay, I now have this space spanned by V1 and V2. And I need to find V3. Now I have to make sure that V3 is orthogonal to both V1 and V2. So if I take the space that is spanned by V1 and V2, okay, I can then get this orthogonal vector that is orthogonal to that space. Okay, so if I find the space spanned by those two vectors, then I'll find the vector that is orthogonal to that space that is spanned by those two vectors. So what I do there is I take my vector x3, I project it onto that space, and then what I can do is say x3 minus that projection is going to take me to this orthogonal vector that is orthogonal to that space. Okay, so whenever you do this, it's always easiest to kind of imagine it in a picture, and then you can go ahead and do the calculations. It's very difficult to kind of explain in words. You have to really look at the picture. So in the 2-dimensional case, you can look at my picture on page 1 of the notes. And if you look at example 2 in the textbook, you'll see the 3-dimensional case where they have done this. Okay, but where you find that projection of W2, of X3 onto W2, that would be X3 dotted with V1 over V1, dotted with V1, plus X3 dot V2 over V2 dot V2. Okay, so that is the space that is spanned by V1 and V2, and then we've projected X3 onto it, and that's that projection. And then by doing X3 minus that projection, we can therefore find that vector that is orthogonal to that space spanned by V1 and V2. Okay, so this all follows from 6.3 that we did last time. So extending this, you can go for as many vectors as you need. You get the Gram-Schmidt process. I won't give you too many vectors in a basis, okay? It's going to be 2 or 3. Going past that, you could be there a while trying to figure this out. So I try not to give you more than about 3 vectors in a basis, just because then it gets very, very long and tedious to do this. But if you are given a basis, we'll say it's a p-dimensional space. Okay, so you've got this p-dimensional subspace of Rn. Then you can create this orthogonal basis instead for W, which is this. And you can keep going all the way down. So VP would be X, that would be that P vector in that basis. And you can go all the way along doing this. Okay. So once we've found this, okay, we can go ahead and do this for any p dimensional subspace of Rn, okay? Now, if you do, this will give you an orthogonal basis. So V1 through Vp is an orthogonal basis. Of W. If you need an orthonormal basis, okay, just go ahead, once you've done this Gram-Schmidt process, go ahead and divide each of the vectors V1 through Vp by their magnitude, okay? So just go ahead and divide by their magnitude, so you square each of the entries, add them together and square root, okay? Divide each of the vectors by that, and that will give you an orthonormal basis. So depending on whether you need an orthogonal or an orthonormal basis, you can go ahead and do that, okay? You can also use this Gram-Schmidt process for something else called the Qr Factorization of Matrices. Okay. What this does is it takes an n by n matrix A and it splits it up into two vectors, Q and R. A is going to have m rows and n columns, okay? So we know already, okay, that the n columns of A are going to span the column space. But what I'm going to ask here is that all the columns in A are linearly independent. Okay, so you've got linearly independent columns in A, and I know that those n columns span the column space of A. Well, if they're linearly independent, I can say that they form a basis for the column space of A. Okay, because they span and they're linearly independent. Now, Q is just going to make the columns of A orthonormal, okay? So instead, we're going to end up with an orthonormal basis for the column space of A. So Q is made up of columns that form an orthonormal basis for the column space of A. What does that mean? Well, what I'm going to do is I'm going to do my Gram-Schmidt process on the columns of A. Okay, so take each of the columns of A, take that as a basis for the column space of A, which is, it will be a subspace of Rm. Okay, you're going to go ahead, that is your basis for the column space of A, but I want an orthonormal basis for the column space of A. So what am I going to do? I'm going to perform the Gram-Schmidt process, which will give me an orthogonal basis for the column space of A. And then all I have to do after I've got this orthogonal basis is divide each of the vectors by its magnitude, and that will give me an orthonormal basis. So Q is just made up of those columns that form an orthonormal basis for the column space of A by using the Gram-Schmidt process and then dividing each of those vectors by its magnitude. R is a weird vector, it's a weird matrix. What it is it's just an n by n. So Q will be m by n still. R is n by n, so it's a square matrix. It's going to be upper triangular. And it's going to have positive diagonal entries. Okay. The reason behind this is there's a very long way of doing this and there's a shorter way of doing this to find R. When you do this, okay, you're basically doing a version of the Gram-Schmidt process. So if you took each of your columns of A to B, let's say an xi, so A is made up of x1 through xn, and then Q is instead going to be the orthonormal basis for that column space of A, so we'll call them v1 through vn, okay, where those vectors are going to be orthonormal, okay. Now, if you think about this, each of the xi's, okay, is going to affect the corresponding vi from our Gram-Schmidt process, okay. So to figure out each vi, let's say we're figuring out vk. Vk is going to be xk minus some linear combination of the previous vi's. Okay, so vk is going to be xk minus something times v1 plus something times v2, all the way up to something times vk minus 1. So each vk is dependent on xk and the previous vi's. So when you go ahead and do this, okay, and you figure out A is equal to Q times R, what you're effectively saying here is that each column of Q, okay, is going to be some x column, so vk is going to be xk minus all the previous vk's. So that means that your entries in R can only be on the diagonal or above, because that's the only columns of Q that it's going to affect. Okay, because anything below that diagonal is going to start affecting like the vk plus 1, vk plus 2, etc. That's what it's going to be multiplying. And they are not involved in the calculation for vk, which means that R must be upper triangular. They've got the full algebraic proof of this. I think it's on page 359 if you would like to look through this. I've also got more of an algebraic proof in my notes, just kind of like a short and condensed version of what I've just said. But just be aware of the fact that it's all to do with the fact that when you do the Gram-Schmidt process, each vk only depends on the previous vi's and xk. It's not dependent on vk plus 1, vk plus 2 up to vn. So therefore, or vm, sorry. So therefore, you know that there is no way that those can have any non-zero coefficients. So you know that the lower diagonal part, the lower triangular part of R must be 0. Okay. So how can we find R very simply? Well, we know that Q is an orthonormal matrix. So for an orthonormal matrix, we've already said in a previous chapter that for an orthonormal matrix, take the transpose of the matrix times itself will equal the identity. So if I do Q transpose times A and do it to both sides of this equation, I'm going to get Q transpose Q times R. Well, Q transpose Q is the identity, so that's just going to equal R. So to find R, all I have to do is find Q first using the Gram-Schmidt process, and then by dividing each vector by its magnitude. And then I transpose that matrix and multiply it by A, and I will figure out what R is. Okay. Now, if we take this matrix, I'll do a quick example of this. If I take A is equal to 310865, okay, then I've already found from before that if I let W equal the span of these two vectors, where these two vectors form a basis for W, I've already found previously that an orthonormal basis, or an orthogonal basis, sorry, for that space is 310 and negative 135. Okay. So if I want an orthonormal basis, I can say, okay, take each one of these vectors and divide it by its magnitude. So I get the square root of 10 by doing 3 squared plus 1 squared is 10, and then square rooting. Okay. So this is now an orthonormal basis for W. So I can say, okay, Q is the matrix that's made up of these two vectors as its columns. So if Q is that, I now need to find R. Well, R is just Q transpose A. So if you transpose this matrix, so each of its columns becomes a row, and then multiply it by A, which was this matrix back here, I'm going to find R. And R comes out to be the square root of 10. Then I've got 30 over the square root of 10. You could simplify that down by multiplying top and bottom by the square root of 10. You'd come out with 3 square root 10. And then 0 and the square root of 35. That is R. And what you should find is that A is equal to Q times R. This thing here has columns that form an orthonormal basis for the column space of A. And this thing is just an n by n matrix, in this case 2 by 2, which is upper triangular and has positive entries on its diagonal. Okay. So it should be pretty simple to do this. This is very, very useful when you do anything computationally, like on a computer, because it does save a lot of memory doing some of this stuff, especially when they're trying to find bases for stuff and all that kind of thing. But we'll look more into this as we go further through it. But just be aware of this process and kind of get used to doing some of these practice problems, and then we'll look more at its uses later on in terms of coding and stuff like that. Let me know if you have any questions. Most of this is just going to take some practice, but hopefully it's not too bad once you get the hang of it. But please ask me any questions that you have, and I will see you in the next video.